Hello and welcome to another lovely edition of the program Teaching and Learning on Radio. Teaching and Learning on Radio is a program that comes your way every weekday on Prestige FM and some other radio stations. And it's brought to you by the Ministry of Education right here in Niger State. We have lots of subjects that we treat every week, every day of the week. We always try to see how we can give the students at home another opportunity to learn while they are home. You know, the pandemic is everywhere. The coronavirus pandemic is everywhere. And so the shutdown and the closure of schools and companies actually made the students are at home right now. Those preparing for WAEC, NECO, and other examinations, I think it's an opportunity for them to stay at home and learn while listening to radio. The teachers, the facilitators will be right here in the studio with us. They will tell us about a particular subject. They look at a subject and a topic, and the phone line will be open for you to actually call in or probably send a message and ask your questions, and you will definitely learn something. So, well, it's for students at home, and it's brought to you by the Ministry of Education right here in Niger State. Teaching and Learning on Radio. Teaching and Learning on Radio it is. Well, today we have lots of things to learn, and we have our facilitator in the studio. You're welcome.
Listeners at home, this is another topic for the week, which is elastic properties of solids. Elastic properties of solids is a topic generally in SS1. We recapture in our SS2 also. And this is a topic that is very important, especially in the aspect of our final year examination, because it entails carrying practicals and essay. Now we're going to look at the objective, what we achieve at the end of the day. First and foremost, we are going to understand what elasticity of a material is all about. Then we also know the law that involves this particular topic, which is Hooke's law. Then the third one is also to explain certain concepts or certain terminologies like strain, stress of young modulus of a material. Then the last one, we're going to look at some simple problems or simple calculation that are involved in this particular topic. Now, starting with the first objective, knowing elasticity of a material. What is elasticity of a material? Elasticity of a material is simply defined as if a material is being stretched or compressed or twisted or bent when an applied force is on it, and that material now regains its size and shape after being deformed. We said this material is referred to as what? Elastic property, or elastic properties of material, or elasticity of a material. A good example of this material is a spiral spring we use in our laboratory. You see, when a load is being attached to a spring, we can see it being stretched. By the time you release the load again, it gets back to its original shape and size if the load does not exceed what we call elastic limit. We are going to explain that concept also. Now, getting to know what elasticity of a material is all about. There is a scientist that worked on this. He performed an experiment using what we call a spiral spring. Like I said, he added load to this spring. He continued to add load on this spring. The spring continued to extend. Now, he continued to add the load. There is a point where if this load is added and that which goes beyond that point, we say this material will not regain its size and shape. And this scientist, like I said, is an English scientist called Robert Hooke. And this Robert Hooke says that provided the elastic limit of a material, that is a material which is elastic, example rubber, is not exceeded, the extension is directly proportional to the applied force. So that's what the Hooke's law is all about. I repeat the law again. That provided the elastic limit of a material is not exceeded, the extension of that material is proportional to the applied force. That is Hooke's law of elasticity. In calculation or mathematically, we say force is directly proportional to extension. Now, by removing this constant of proportionality, we say F is equals to Ke. This K is what we refer to as stiffness constant or elastic constant. Now, making K the subject of the formula, we say K is equals to F all over E. this F, the force, which is in Newton, and the E, which is in meter, which is the extension in meter, that the unit of this constant of proportionality is Newton per meter. So this has explained what Hooke's law is all about. He performed an experiment using a simple spiral spring loaded with weight, and at the end of the day, he discovered that provided the elastic limit of that material is not exceeded, the force will always be proportional, directly proportional to the applied force. The force is directly proportional to the extension. Now, having stated this law, there is a chart here which gives us a graph of load against extension, because here the man talks about load and extension, the force and extension. Now, at the end of the day, this is just a material now. The material is a spring. When a spring is loaded, you are plotting the graph. You see, it is a straight line graph up to this point A. This point A is referred to as proportional limit. At this point, we said the load and that is the force and extension are proportional. That is, if there's increase in force, the extension will always increase, and at the proportionality, this wire will remain elastic. Now, at point B, this wire we said it is at elastic limit. Now, according to this Hooke's law, it says if that limit is not exceeded, the material will still regain its size and shape. Now, we said this wire will still remain an elastic material at this point B, because we said based on the law, it is being obeyed. But at point C, which is what the yield point, that is where the deformation of the material comes in now. By the time you apply load again beyond this elastic limit, we said this material will be deformed. What do I mean by deformed? It will not cut, but rather when you release that load, the material will not regain its size and shape. So that is point C. But point D and point E, or at this point, the material is already completely out of use. And when you put more load, that is at E, it breaks down, and that is all. You cannot enjoy that material. This is exactly what came out in your JAM this year. They were asking you of this point, where the limit beyond, which this elastic material cannot go beyond, and many people were confused, giving C, which is wrong. The yield point is the deformation point. So take note of this, please. This is what mostly is referred when it comes to examination. This is what you continue to see. Now, after explaining this point, there are some terminologies that we use again in this topic. We have what we call the tensile stress and the tensile strain. The tensile stress is defined as the ratio of force per unit cross-sectional area. That is the diagram I've just put it in. When you apply a force to an elastic material, you see there is extension being produced. This force per unit cross-sectional area defines what this tensile stress is all about. So we say force per unit cross-sectional area. And like I said, the force is measured in Newton, while the cross-sectional area is measured in meter square. So the unit of tensile stress is Newton per meter square. Then we also what we call tensile strain. This tensile strain, based on this diagram also, we say it is being referred to as the original length. You can see from this point to this point is L0. The original length all over what? The extension. So when we have the original length of the material all over extension, we say we have what we call tensile strain. And this has no unit, because meter cancel meter, 0, is that not? So listeners at home, will this, a scientist also proposes this using that particular activity. And this scientist is what we refer to as Young modulus. The Young modulus of a material is this tensile stress all over tensile strain. So by definition, we said F all over A into L naught all over E. So this is what we refer to as Young modulus of a material. Now if you want to do it mathematically, you want to rearrange, we say force per unit cross-sectional area is equal to extension all over what? Original length. So this is what we refer to as Young modulus of a material. Now having known this, there's another important thing in this particular elastic properties of a material, which is the energy stored or the work done in an elastic material. The work done here, what we refer to as work done, is simply the force you are applying on this elastic material. You know, you are applying the force. It now what? Extends the material. Releasing the force, the material rod goes return back to its original. So the to and fro. So the work done here will be defined as the average force multiplied by what? The extension of that material. So which is the same thing as energy stored. Average force multiplied by what? The extension. And that's what gives us the formula of work done or energy stored in an elastic material. Here is a half Fe. Like I said work done or energy stored is the average force multiplied by what? Extension. The average force is F all over 2. Refers to average. Is that not 0 plus F all over 2? So the same thing as F all over 2 or a half all over 2 multiplied by E, which is the extension. Now, from Hooke's law, we still have to define this F. From Hooke's law, we say F equals to what? Ke. So we have to substitute the value of F into this equation. And in doing that, we say F will be equal to half Ke squared. So this is another formula to calculate the energy work done or energy stored in an elastic material. We have two formulas here. If the force is given and extension is given, you use this. If the stiffness constant and extension is given, you use this. So this is what we refer to as energy stored in a particular material. Now let me solve one question here. I have a question here for us to solve as an example. I'll read the question out. A force of 20 Newton extends a spring of natural length 2.5 meter by 0.5 meter. What will be the length of the spring when the applied force is 35 Newton? I'm not going to write the question, but I'll give you the data here. The data here we have, according to the question, that the force is 20 Newton. Then the spring, the force extension is 2.5. That is the main extension. Then the other extension is 0.5 meter. Then another force that is being applied after this is what? 35. So F2, let's say F2, this is F1, 35 Newton. Now they say what will be the applied force, what will be the extension? Or what will be the length if the applied force is 35 Newton? Here the first thing we do, we now use what we call Hooke's law. The formula of Hooke's law, F equals to what? Ke. Here we are going to look for the stiffness constant since the extension is given. Now we say F, our F is 20 Newton. The stiffness we don't know. Our extension is 0.5. Now when you do this, K equals to 20 all over 0.5. What will it give us? Class, 20 divided by 0.5, 40. Is that not? We have what we call 40 Newton per meter. That is the unit of stiffness constant. Now we move to the second one again, because there are two forces given. We go back and say from F equals to Ke. Here the force is given as 35. We have the K. The K is given as 40. The extension is what? So what we do here, we now say extension is equal to 35 divided by 40. When you do it very well, you get a 0.875 meter. 0.875 meter. Now, the real length will now be E1 plus the final extension. So our length now will be equal to E1 plus the E2. And this E1 is what? 2.5 plus extension size 0.875. And this will give us what? 3.375 meter. So this is our final answer. Now, class, I'll have to take this. I will not go back and summarize my lesson. From the lesson, we define what elastic properties of materials are all about, which I said that any object that is being stretched, compressed, twisted, or bent, and at the end of the day, it returns to its original shape and size, we said that material is referred to as what? Elastic. It has an elastic material in it. Then I went further to discuss what the Hooke's law is all about. I said Hooke's law, that is to say, provided the elastic limit of a material is not exceeded, the extension is always directly proportional to the applied force. After knowing that, we look at the sketch, that diagram of load against extension. We are able to see at the limit at which this material is being exceeded. At point B, that is at the elastic limit, anything beyond it, we say that rubber is being deformed. Exactly. Then we went further to look at the Young modulus using that chart. And the Young modulus of material, these two things are defined there: the tensile stress and the tensile strain. The tensile stress, I say, is the force per unit cross-sectional area of the material with the unit Newton per meter square, and that tensile strain is extension all over or extension of original length. Is that clear? So that we also look at the energy stored in an elastic material, and I said energy is the average work done multiplied by what? The extension. And we said the energy stored, we know the unit is always in joules. So we said if you do that again, based on Hooke's law, you can still break the force to be equal to Ke. So we have a half Ke square or a half Fe. So that brings us to the end of this lesson. Listeners at home, I have a question for you. State Hooke's law. Then B, define tensile stress and tensile strain. Then the last question is calculation. It was observed that when uniform tension of 80 Newton was applied to a string of length 4 meter and uniform cross-section of radius 1 millimeter, the string extended by 2.0 millimeter, assuming that the deformation obeys Hooke's law. Now determine the energy per unit volume of the string. Take this question. Now with this you can join us on WhatsApp with this number 09029282040. Again, 09029282040. Thank you for listening.
That was a wonderful presentation by our facilitator. He taught us a whole lot, and I learned as well, so I believe you've learned something this lovely edition of the program, Teaching and Learning on Radio. Well, join us again next time, that's tomorrow. Join us again and for another lovely edition of the program. You never can tell the subjects coming up, so just be on the lookout. And children out there, and not just children, parents, I urge you to encourage your children to listen to the program. As they stay at home, they learn as well. All right, thank you so much for watching and listening. Bye-bye.